Hello, welcome back. In this video, we're going to go through another application of differentiation. We're going to try to find intervals on which a function is increasing or decreasing. So the given function is sine x minus 8, and the given interval is 0 and 2 pi. Let me just remind you the test for increasing, decreasing functions. So if you have a continuous function on the closed interval a and b, and differentiable function on the open interval a and b, then by looking at the sign of f prime, you can determine whether f is increasing or decreasing. For example, in the first case, if f prime is strictly positive for all x in the open interval a and b, then the conclusion here is that f is increasing all the way on the closed interval a and b. If f prime turns out to be strictly negative on the open interval a and b, then the conclusion here is that f is decreasing on the interval a and b. And if f prime is 0 for all x in the open interval a and b, then the conclusion here is that f is constant on the closed interval a and b. In order to apply this test for the given function sine x minus 8, we first have to verify that f is continuous and differentiable on this interval. So our function consists of two components. One is sine x, the other one is 8. And both functions are continuous and differentiable over the real axis. So in particular, f is going to be continuous on the closed interval 0 and 2 pi, and differentiable on the open interval 0 and 2 pi. So we can go ahead and find f prime and determine its sign, and we can get the conclusion of increasing or decreasing behavior of f over the interval 0 and 2 pi. For this purpose, we need f prime. So why don't we find f prime here? Well, since f prime consists of two pieces, we're going to find the derivative for each piece here. So the first piece, the derivative of that, and the derivative of the second piece. Well, you can use the differentiation table or formula card to find the derivative of sine. That is in fact cosine. And the derivative of 8 is just 0. Okay? So we have f prime exactly equal to cosine x. So now the question turns out to be, what is the sign of cosine x over the interval 0 and 2 pi? And remember that the graph of cosine fluctuates in between -1 and 1, and cosine takes positive and negative values in the subintervals of 0 and 2 pi. So to determine the sign of cosine in the subintervals, we need the x-intercepts of this function, or in other words, x-intercepts of f prime. So what we're going to do next is to set this to 0 and solve for x, and those x-intercepts are going to tell us that the function goes from negative to positive or from positive to negative. So our interval is 0 and 2 pi. You can perfectly use the unit circle for this purpose. So go to the unit circle and check which x values and check which points provide the x entry to be exactly equal to 0. And here is the unit circle that we recall from the pre-calculus section of this course. As you see, we were looking for points whose x entries are 0. Well, here we go. I have one here, another one here. So from 0 to 2 pi, that's one full revolution. And pi over 2 and 3 pi over 2 are only degrees for which the cosine achieves 0. In the next part, we have the endpoints 0 and 2 pi, as you see. And we got 2 points coming out of solving f prime is equal to 0. These are pi over 2 and 3 pi over 2. So now I have 3 subintervals. So one subinterval is 0 pi over 2. And the next one is pi over 2, 3 pi over 2. And the last one is 3 pi over 2 and 2 pi. So the next step here is to determine the sign of f prime across the x-intercepts, pi over 2 and 3 pi over 2. So for that purpose, I'm going to choose sample points on the left and on the right of the intercepts. And based on the value of f prime, I'll conclude about the sign of f prime for those subintervals. So calculation-wise, we're going to evaluate f prime at pi over 4, and go ahead and punch in cosine of pi over 4 because f prime is cosine x. Let me just write that down here. Right? So f prime of pi over 4 is cosine pi over 4, and this is f prime of 3 pi over 4, and finally this one is going to be f prime 7 pi over 4. In other words, again, you're punching in cosine pi over 4, cosine 3 pi over 4, in cosine 7 pi over 4, and don't forget to set your TI-84 to the radian mode before you calculate those values. And here is the result. So f prime at pi over 4 is going to be something positive because you're in the first quadrant. And f prime for 3 pi over 4 is going to be negative. So it's going to be a negative number. And f prime at 7 pi over 4 is going to be positive. So by just choosing our sample points, we determine the sign of f prime on the subintervals. And by the way, you can choose different sample points depending on your taste. Okay, so these are my sample points, and your sample points could be totally different. But obviously, you're choosing sample points in a way that those points should lie in the corresponding subintervals. And the test for increasing and decreasing functions implies that f is increasing on this subinterval, decreasing on this subinterval, and increasing on this subinterval. So across the x-intercepts of f prime, the behavior changes from increasing to decreasing and decreasing to increasing. And to verify our table, here is the graphical outlook of the function. And the interval was chosen to be 0 and 2 pi for this function. Well, as you see, between 0 and pi over 2, the function keeps increasing. And we hit the x-intercept of f prime. So we get to a point where f prime is 0. That means we have a horizontal tangent line. And once we hit that, that means we made a peak here. So we start decreasing all the way till we hit the next x-intercept, which is 3 pi over 2. And at that point, f prime is 0. We have a horizontal tangent line. And then after that, the function starts increasing all the way. And our table is verified by this graph, and that makes the end of the video. So thanks for watching. I'll see you in another video. Bye.